We're now going to start on a very important piece of algebra that we use extensively in mathematics and physics, which is the use of imaginary and complex numbers. And we start this by talking about the square root of -1. So in ordinary real numbers, no number multiplied by itself gives a negative result. So 2 times 2 equals 4, but also -2 times -2 equals 4. Equivalently, there is no real square root of a negative number. There is no number that we know of as a real number that when multiplied by itself will give us a negative number. However, we can choose to define an entity that we call the square root of -1. And if we define that entity, we can write square roots of negative numbers. And the reason for doing this is really a purely practical one. The result of doing this is we obtain a very useful algebra, an algebra that saves us a lot of time and effort. So let's just choose to define this entity I as the square root of -1. So that means that I squared is -1. And also minus I squared is -1 because the minus times a minus just gives us a plus. So again, we end up with I squared, which is -1 by definition. Incidentally, it's very common in engineering to use the notation J equals the square root of -1, and there's nothing wrong with that notation. In what I do, I will use I because I'll be following mostly the physics conventions. But J is another way of writing square root of -1. And I think in electrical engineering, it avoids the problem of confusing the I with an I that might represent current, for example. Any number that is proportional to I with some real factor multiplying it is called an imaginary number. So 4 times I, which I've just written here as 4I, or some other number, 3.74 times I, or I times pi here. These are all imaginary numbers. It's common to put the I after numbers written out, like 4 or 3.74, but to put it before variables or other algebraic constants, but it doesn't matter which way you do this. This is just a convention. And we note that we can write the square root of any negative number using I. So the square root of -4 we could write as the square root of -1 times 4, which would be the square root of -1 on its own multiplied by the square root of 4 on its own. So that would be I times 2, or you might conventionally write that as 2I. When we put together real numbers and imaginary numbers, we get complex numbers. So if we consider some now complex number g here that is made up out of a real number a plus I times another real number, I times this other real number is now an imaginary number. So the total number g is called a complex number. It's got a real part, which is a, and we write that as re of g here. And it has an imaginary part, which is b, the part that is proportional to the square root of -1. So a is called the real part of g, b is called the imaginary part of g. And we use this notation, the re and the im. The complex conjugate of a complex number is the number with the sign of the imaginary part reversed. And we indicate this complex conjugate usually with a superscript asterisk here. So if g was a plus ib, then g star, or the complex conjugate of g, is a minus ib. So we often call this asterisk a star. Now, multiplying g by its complex conjugate gives us a positive number, which is called the modulus squared of g. And the positive square root of this modulus squared is called the modulus of g. So This is the modulus squared. It's g times its complex conjugate. Either way around, it doesn't matter. We use these two lines here, which are often used to represent a modulus, and the square, of course. And as I said, the positive square root of this product we would call just the modulus of g. That's the positive square root of this modulus squared of g. Let's look at some important complex number identities. We note that for the modulus squared, which of course we can write as g star, we can also write that out as a plus ib times a minus ib. And of course we can multiply that out. So a times a gives us the a squared here. The ib times the a gives us our ib times a here. The a times minus ib gives us minus iab here. And the ib times the minus ib gives us the minus I squared b squared. And of course, since these two terms in the middle cancel, we have a squared plus b squared. In other words, we have this important identity that the modulus squared of a complex number a plus ib equal to g is a squared plus b squared. For the reciprocal of a complex number, it's not immediately obvious that this can also be written in a form like a plus ib, but it can be. So if we have a number that's 1 over c plus id here, we can multiply by c minus id on the top and bottom lines. We can multiply out this bottom line, that just comes to c squared plus d squared. And so we've managed to turn this number here, which was 1 over a c plus id, into some number that is an a plus an I times a b. So the reciprocal of a complex number can also always be written in the form a plus I b. In this case, it's a minus associated with this term, but it's still the same form, an a and a b here. So just writing that out, the reciprocal of a complex number can also be written in this same form with the real part and the imaginary part. The imaginary part here is minus this stuff here. Still a sum of real and imaginary parts.